Okay. So in terms of what I kind of wanted to go through today, we'll start with the concept level, just a little refresher about reinforcement learning. And I know we mentioned in the agenda of this meetup is that we'll talk about hierarchical reinforcement learning. And that will also be just from an architecture concept perspective. So we'll go through some like basics of that. And then what is really interesting about HRL is how that is being transformed into this concept that's used very often in like agentic platform, like how to have different LLM agents working together. So the popular paradigms like task planning, task decomposition, and tool use. So we'll talk about these as just a few examples. And then there are, I think, 3, 4, 5 case studies I wanted to share, including like vibe coding, just like autonomous agent handling tasks. And then like computer use is another one I wanted to share as well. So yeah, that's basically what I wanted to cover. Before diving in, maybe just like getting a pause check from the group, just looking at this, is there anything particular that you wanted to hear more or less, or maybe just give me some feedback before we jump into the content. Refresher of reinforcement learning. So as I start to, so every time I think about like how to explain to people what is reinforcement learning, like starting from the very basics, and then plus like some terms that's really popular, right? So I kind of tie it together here and then like put it in 3 buckets. One, of course, we need to understand that reinforcement learning is basically there is an agent that is trying to do its best in an environment. And the training, the policy is what we're trying to optimize, like by letting the agent learn. And the way that to achieve that is having this objective function. So basically, agent would, given a state, agent will know what action to take, and that action environment will basically give a reward based on what that action takes. And with that, this entire thing moves to the next state. So if you think about like in the traditional way of using RL, it could be like navigating a room, like completing a task, right? Go left, go right. That is a numeric or distinctive space that we're talking about. Or in the recent LLM domain, then the state would be like, what was the last word? What is the current word? And what's the next word we're trying to generate? And that's basically making it an episode or a sequence of the states. So that's the like a vanilla version of the RL. By optimizing the policy or like optimizing the ability of the agent, there's a very famous method or architecture in the RL is what we call the actor critique method. So in that, basically, we break down agent and let it specifically have 2 steps or 2 components. One is what we call the actor that still does the job of like making sure update the policy and optimize the policy. But then the actor is being helped by a critique component that will basically generate a value function and do the comparison and generate a value called the advantage, and use that to basically get this whole optimization process more stable. So that is being a very popular architecture in the RL domain. So if you hear terms like PPO, it's one of the actor critique methods. And then RLHF, which is crucial in what we see in today's a lot of foundation LLM models, is because like if you if you train just a language model with autoregressive, then what it's gonna be able to do is just complete a sentence, right, or generate the next word. But more and more, we've seen in the models in LLMs is like its ability to reason, ability to complete a task, ability to do things. So these are all different behaviors that's being like post-trained. So there's the pre-training and there's the post-training. And the RLHF is a very, I want to say, standard now method or learning paradigm that's being used to facilitate that process. And because it is so popular, so I thought we would just maybe take a minute to like deep dive into that. Still like staying in the refresher of the basics section here, but if we look at, and this is a diagram from Instruct-GPT that highlights or outlines how is that learning happening for the as the GPT model gets trained. So step number one is how the supervised fine-tuning learning paradigm is being used, and how by the end of that, there is like a one set of the policy, and basically the weights are generated. So that's step number one. And step number two is how a reward model gets created. And then in the step number three is where we see like methods like POO like will be used to optimize the policy and generate the final or trained weight. And then what we saw in the like actor and critic, that component is basically how the POO like is built in inside of that method is where to find that component. So throughout this process, we basically incorporates the human input and then update the weights of the model, and that's how we like. If today we just use a foundation model and don't even do any fine tuning on top of that, right? It's already very general and has the ability to complete a lot of tasks. It's because it's followed this process. It's being trained to complete a lot of things and more like following the guidelines, the safety guidelines and all that, right? More tuned to the best behavior aligned with humans' need. So it's all following this process. So with that, before talking into the jumping into the hierarchical reinforcement learning
Follow
architecture,
the spec codes and add them up.
Because we'll talk about how we have like different levels, right, in the RL process. I thought we would wanted to go back to the vanilla version, right? Vanilla version of the RL. There's an agent, there's an environment. On the right, you will see a simple example. This is to say, like, there's a person that every morning he wakes up, he starts from home, and he will go get a coffee, and then go to office. And then he can choose to chat with the colleagues, the coworkers. He can choose to go back to the computer and work. And at the end of the day, he will leave office and go home, right? It's that process. So in here, in this environment, you see from state to state, home, coffee, chat, computer, right? These are all different states. There's a distribution of the probability assigned to how the state moving from one state to another, right? It is assigned to that. And then there is a reward. So reward is being assigned and designed. So like if we apply our learning and training on top of this, by the end of the day, we would have a quote unquote agent that is able to optimize this daily routine, right? What you see down below, right, the sequence of how things are happening, like from state to state, right, is the episode for this environment. Again, like in the LLM's world, we would basically see these as a sequence of the words, right, a sequence of the tokens. So it is how this is being applied to the language model. Now, with that, what hierarchical reinforcement learning is trying to solve or say is, so there is a sequence of the actions that will move us from state to state. And of course, we always wanted to reach the target state, but to complete that entire process, it basically is like exploring. So how do I make that exploration process or training process or optimization process efficient enough and fast enough is why we're trying to separate or generate the abstractions here. There are basically two types of abstraction. The one that you see on the left is by step, by like it's called temporal, and the one you see on the right is like maybe we don't know how long it takes for each of the chunks, but we wanted to give it a definition or just chunk it off by state, regardless of how the sub goal or the sub task would take. So the one on the left, just because this, I like this diagram, it kind of tells a good story here, is so if there are 4 states, we wanted to choose to bundle the state 2 to 3 action as like one, and then abstraction. We basically abstracted that into a sub goal and subtask. So in the middle diagram, you can see that by doing that, it basically makes the exploration much faster, right? To reach the target goal instead of like being quote unquote trapped in that neighborhood on the top left corner, right? Our agent with this hierarchical structure and the breakdown is able to explore the spaces faster and broader. The state abstraction, it's similar to that, but just have more defined meaning of the state. In this game's example, we could say, let's just define if agent has key. Based on yes or no, the sub task will be go get a key, right? Like go get a key, it can be like going to the left and down and left. But that left, down, and left action is being contained in the get key state. And it's being assigned to a worker level agent instead of the agent that is, we'll see the next slide is called manager agent, that is basically breaking down the tasks. This is just another like architecture to kind of illustrate that idea. On the left, a simple version of architecture is that we have an environment, and there will be that manager on the top that will choose an option. So basically, the manager's policy or goal or task for that agent is to get the best policy to choose the right option given the state. And regardless of the options being picked, the worker at the low level would only need to optimize its policy to complete the task. And once that is completed, the manager and the worker together marks the complete of this iteration, and then the actions being generated, and the entire thing moves to the next state. What you see on the right is just one example of how this architecture is being implemented. Between the higher level and the lower level, or the manager and the worker, it's a goal function that's being passed around. But this really just mimics what you see on the left, which once the worker is done its job, then that only completes the iteration and then generates the action and moves to the next state. So with that, you can see already that there are 2 policies basically. So the manager has its own optimization job to do, and the worker has its optimization jobs to do. So to train this, it will basically take like the 2 loops to complete this. And the design of like how to chunk the different options, that is very task specific. So like if it's different from what LLM would have, like which is a generalist, this type of architecture is useful or method is useful if we have a very specific task in mind and we wanted to carefully build the architecture of it and then right optimize the success rate. So with that, I wanted to then transition from this and let's start looking at how, because we're talking about agentic, right? Like how in the LLMs world, how that agentic, I guess, architecture is borrowing the concepts of hierarchical reinforcement learning, although like in the training, in the specific training and model generation steps, these are like totally two separate concepts. But just from an architecture perspective, I find it very interesting that they are kind of borrowing the ideas. This is the survey that I will use to guide the conversation for the next few slides. Because I like how it mentions like the tool use, the planning, and the feedback learning, which are some very popular tasks that like popular applications today are trying to solve. The way that this is structured is instead of treating LLM as one box and trying to let one LLM do everything, we can deliberately design an architecture and say one of the LLM or agent is that policy. It's trying to optimize the policy. And we can put, for example, another LLM as an evaluator or an LLM as dynamic model that can do the search against a tree. So these are different roles and quote unquote profiles that we can give LLM in our design. So across the different popular paradigms here, we see like these roles and patterns being applied. So they kind of work in conjunction with each other to complete the task. So we can go through them one by one. We start with tool use and zoom into that little diagram that we had in the last slide. What this is saying that there's an environment that the LLM or the agent is interacting with, and there's a bunch of tools that the LLM has access to. So in two distinctive steps, and then like RAG, for example, works in this format. And so you have the environment, someone like chatting, for example, was the LLM serving as a policy model. And the LLM will, in RAG's example, will trigger the document retrieval algorithm or process. So then the document being searched and retrieved is, you see the purple or the pink arrow feeding back into the LLM. So based on that, then LLM generate the response and take the action back to the environment or the user. So that is an example of how LLM is using the tool, right? Like using a document search for Q&A. Here is just like more examples of how we can architect the tool use. The one that we were saying on the RAG part is more like the second one. So the third one that you see there is just a black box, like leaving it to LLM to make the decision on which tool to use. The one on the far right you see is let the LLM serve as a policy, and we on the side also stand up an evaluator or a judge to critique that action, and then based on that over time, right? If it passes the evaluator's criteria, then that action gets taken. So these are some patterns for the tool use. For planning, or sometimes we call this like task decomposition as well. So even without like specifically designing or architecting these, like in today's foundation models, like for example, if you chat with ChatGPT, it already is quite well at planning things, right? Say I wanted to say grocery shopping. Like, can you tell me what to do, right? That essentially is just like planning. It gets really well already. But in case the type of planning task that we're talking about here is very specific, because in the enterprise level use cases, these are specific business rules and workflows that we're talking about. Then that planning, we can design it as like a more architected and like graph kind of in this you see like a search against the graph, right? So as we design that and then apply LLM on top of it is how we get to see more and more optimized performance on completing a planning type of tasks. The last one, because we talked about to use, we talked about planning. The last one is kind of similar to what we talked about earlier, is on the learning from the feedback, like human evaluator or AI judges. Either way, right? It's having an evaluator here. The one on the left is basically how the RLHF style is working, is us incorporating human evaluators critique and rewrites. On the right is we stand like things like we stand up a AI judge, right? Would be LLM itself serves as an evaluator. So with what we've seen in the past, like 4 or 5 pages or slides are basically just ways we're decomposing the task, we're decomposing the roles, and then like letting different LLM models work together to complete a task. If we think again about what we saw in the hierarchical reinforcement learning, so I kind of put the side by side of what we've seen in one versus the other. And then like again, like going through this list will help just like go through the principles, right? Because there might be very customized applications you have in mind, and as you design your own agentic AI or agentic platform to handle the tasks, these are just some like design principles and choices you can follow and make for your use case. So hierarchy design wise, if what we saw in the hierarchical reinforcement learning is a very explicit and hardwired design. So there's a manager and there is a worker, and there's that signal we set up between them, right? And then the training, every iteration has to involve both. Versus if our goal is to train an LLM, and that is basically us expecting this one model to work to its best ability. So yeah, policy and evaluator roles, because hierarchical reinforcement learning is still following that like vanilla, has the flavor of the vanilla RL. So like the evaluation here to the model is really still that reward. But in LLM agents or agentic, we can get more creative, right? We are splitting up the roles so we could have one model be the action taking person or agent, and then like a totally separate model that does the evaluation. The state and observation. So this is an interesting one. So basically, we're saying that HRL is handling the quote unquote simple tasks, and then the LLM handles a lot more, because it's a sequence and of the context we have to ingest into the LLM, or the LLM has to take into consideration. It's good and bad. So the one on the left, because it is very specific, and then it could sometimes just be a very grounded numeric vector. It handles very specific tasks well, and it's well grounded. The LLM on the other side, because it has it's being provided with a very long list of history of the text, right? It starts to get more and more difficult for it to focus. So like the problem we see in hallucination and all that is to some extent kind of because of this as well. The I guess like the one I kind of in my mind are separating these two is really using the engineering effort. The hierarchical reinforcement learning is the method that we're talking about in the learning stage. The LLM, like all the design and the way that we're architecting that we saw in the past few slides, is about how do we inference, right? And things happening in the inference stage. How do we prompt the model and let the model do things already for us. So these are models that's past that learning stage. And because of that, so the concept of the design and the architecting will happen differently. To get the LLM or an agentic platform and model work well is how do we well, here it just says like prompt timing, but it really is beyond prompt, right? It's the choice of all the other tool use and all that API interface as well. But it's how do we, with the interface that's available to LLM, right, how do we optimize the use of that by using architecture? The train time complexity for HRL is we have to understand the task really well. We have to be able to design and decompose and design that business workflow ourselves. It's not necessarily saying that this is a bad method, because if I think about in the business settings, right, a lot of the times the task is very specific. Like there is a very specific workflow already. So instead of using a general LLM to solve it, like making that RL working in a contained and grounded space and format is not a bad thing, right? It's actually more applicable to some of the use cases we would see. And because it is grounded, right, HRL is pretty good at like taking actions quickly. Like the robotics application, right? We see a lot of applications and papers around that. And the problem they're trying to solve is the robotics related problems. The LLM agents are like, we won't see LLM agent. Well, we will see it's in an example, but that is after the elevating the LLM's role to be the high level task manager. But we won't just let one LLM like handle the things like robotics because generating the text that takes time, right? So depends on the frequency that we're looking to achieve. It sometimes won't be suitable for robotics types of action. And again, like we mentioned, the more grounded version is better for the task and specific applications, and LLM more and more, right, is very general now. You can give it any task and it will get somewhere, right? But even without further architecting. Okay. Let me see. So we will get into the case studies very soon. Before for the case study, I'll show a few videos, but before that, this is the last like slides or example on the slide I will show you, and then I'll move away from the page. So in this paper, which is quite recent, it was last year, it's called RL-GPT. It's actually interesting, right? It's following that exact thinking that we have for the HRL. Right here, we're saying HRL is better for quick reflexes, but LLM is like kind of slow. And just with that nature, what this paper is trying to do is let's get the slow agent, the LLM, right, to break down the task. And we'll have the sub-act 1 to 3. And then let's have the fast agent, maybe a smaller model, right, handling the completion of that task. And what the paper explored is following this and then like using this diagram to implement. In the Minecraft game, it finds a diamond relatively fast, right? Is what the benchmark is being used there. So I just found this one very interesting because it definitely just like breaks down and uses the different natures of the or characters of the manager and the worker level, right? Exactly like how RHL defined it. Okay. With that, I wanted to show a few examples because we talk about we'll see the case studies from the real world. This is called Say Can. Let me see if I can. Okay, it works. So what it does, again, this is an application that combines the language model's capability and the robotics problem. And so the language model, once given this prompt or inquiries, as I spilled my drink, can you help? It will generate a list of actions to do. So at a glance, it all makes sense from what you see in that blue box on the left. But for a robot, a physical robot, it will have a different level of like ranking and rating, like what is more feasible and actionable to achieve the task. So this method and idea is basically to combine the two to achieve the best action. So in this example, and there are actually a few more, if you're interested, you can do a search and see the other demos they give, right? It's so basically from the whole list of what a language model will generate, it gives us another layer of filter or ranking to make it more task appropriate. So that is a robotics example. In the next one, I wanted to talk about computer use, which is the model cloud and how it can navigate your computer to complete very specific tasks. And you give it to the model.
I'm Pooja, and I'm a researcher at Anthropic. I'm going to show you a simple example of computer use today. My friend's coming to San Francisco next week, and I want to take him to do some touristy stuff. I think doing a sunrise hike with a view of the Golden Gate Bridge never gets old. So I'll ask Claude to figure out some logistics for us. I'll ask Claude to find a good place to see the sunrise, to help me figure out timing logistics, and help drop a calendar invite so I remember when I have to leave. It's opening Chrome, going to Google, searching, and it looks like it's found something. Great. So how far away is the location from my place? It's opening maps, searching for the distance between my area and the hiking location. Cool. So now it looks like Claude is searching for the sunrise time tomorrow. And is now dropping it into my calendar. And populating it with some details. And great, it looks like Claude did it. This is a simple example, but we're sharing computer use early to learn from what people build.
Okay, so that was one example, and I had to stop share because Zoom muted me and I share screen. There are a few more that I saw really cool. So I picked that one because it's a like task planning. So all the actions you saw there, it was like no human touch, right? No mouse clicking by human at all. It's all done by computer, the computer used by the model itself. So I will show you the next one, which is a live coding using Cursor. Also a YouTube video, so I'm totally just borrowing the ideas from other YouTubers. Let's see.
Cursor is a VS Code fork, and you'll just see this additional plane here on the right-hand side. I'm going to ask this, write a implementation of the game of life in Python, animate the output in the console. You can see here we have different models that we can choose from. Claude 3.5 is on, it's the best for writing code as of today, but you can also use O1, you can use GPT-4o. And you see here that it's going to not only write the code, but it gives some explanation. You can either click this button and copy, or you can click this apply, and they've got a kind of a whole model dedicated to making diffs to your existing code. I'm going to accept them. I will open this in the integrated terminal, and we'll run it, and we have a fully functioning game of life on the first try. This is code that I could probably write on my own. It would take me a few hours. It would not be nearly as succinct, and it definitely would not run on the first try. So just this functionality alone, just simply bringing the chat into the IDE, in my opinion, is worth the $20 a month. Second thing the Cursor did, you can select a chunk of code. I'm here just going to select all of it, and I'm going to press Command K, and I'm going to ask it to make some changes to my code. Double the size of the board, make it green like an Apple IIe. I'll submit that edit. And now you can see a little bit more of that diff in action. So it found where the board was defined, and then down here, it found the color. And so I can click accept, save that, open up the terminal again, rerun my program, and now we have something that looks more like an Apple IIe. So this functionality is pretty incredible, right? You're making changes to your code in natural language, and that's really powerful, not just for developers, but for folks who maybe have always wanted to learn to code but never have. I would say that coding has probably never been more accessible than it is right now. Third thing that is really useful here is debugging. Let's pretend there was a syntax error that for some reason we would not have caught with the other plugins that we might have installed here. I'm going to run this again. I'm going to get my traceback. I can highlight the traceback, and you'll see this button pops up that says add to chat. And so I'll add that traceback to chat. I'll say fix this error. And it identifies the error. It gives me a fix. I click apply, and it applies the fix. I don't have to copy paste the code, figure out where that fix goes. It just kind of takes care of that for me. I run the code again, and it works again. Look, I don't want to overhype this. This is an AI demo, and the demos are always better than reality. We're starting from a blank file here, not dealing with a big code base. We did not encounter any hallucinations, and you will. But there are very real productivity gains here. So if you have not tried Cursor yet, would encourage you just to go to their site, download it, try it out for a week or so, and just see how it works for you.
Yeah, so that one very specifically is helping with the coding exercise. The next one I wanted to show, and then for this one, and maybe we can do this in the other session in the future, because I actually wanted to show it live on my laptop. It's called Manus. The app is called Manus. I had it work with a task I have in mind very specifically, like text filing. It worked really well, but today when I went on there, I realized there's a long wait time because the app is being used by a lot of people apparently. So I have to find another video then. So just to show you how that is. That one is less about coding assistant. It really is an autonomous agent to help with any kind of tasks. But this one is the demo 2 I will start showing here is still like helping build an app. So somewhat falling in that live coding application area. So here we go.
In this example, we have Manus conduct some research. It needs to filter New York properties based on multiple criteria. For complex tasks, Manus first breaks them down and creates a to-do list. Manus begins by searching and carefully reading articles about the safest neighborhoods. Then Manus researches middle schools in New York. Next, Manus writes a Python program to calculate my budget. Based on my budget, Manus filters listings on real estate websites. Finally, combining all the information gathered, Manus writes a detailed report and compiles all the resources. In this example, we have Manus perform a correlation analysis between stocks. For professional data, Manus can access authoritative data sources through APIs. After validating the acquired data, Manus begins writing code for data analysis and visualization. For Manus, coding isn't necessarily the goal, but rather a universal tool for solving problems. It looks like Manus has completed the data analysis and visualization. But interactive data visualization is even cooler, so I asked Manus to create a website based on these data. With my permission, Manus deploys the finished website online and provides me with a shareable link. Let's see what Manus has created. What you've just seen is just a small sample of what Manus can do. In fact,
yeah, if you're interested, I actually find the Manus to be very interesting because I used it for a few things. Like text was one thing, and I also used it to just like build a dummy app that I had in mind. And like the website, the app it created, it actually works. And I can so like wait after 10 minutes, the first iteration comes and they're like something on the UI not working. So I just need to prompt it and say like, can you fix the spacing or make things like aligned and centered? And it knows how to debug for it on itself. And I'm just saying the next iteration, it works again. So yeah, really cool.